Welcome back. In this lesson, we're going to take a look at transformation of linear functions. You're going to enjoy this mostly because it's super short and requires virtually no writing. And by virtually, I mean like we're not writing anything down. But there are some important concepts that I want you to get across here. The reason that I will say it's so short is because transformation of logarithmic functions is kind of like transformation of any other function. All the same rules still apply. There's just one special little thing that can happen that I wanted to show you. So let's pop over to the lesson really quick. And much as I just said, these are like all other functions. All other functions act the same way. They can be stretched and compressed horizontally, stretched and compressed vertically, flipped either way. A whole bunch of things can happen there. They can be slid left and right, up and down, but the rules are always pretty much the same. I will point out there's a little challenge problem down there for later, but you can try that on your own. What I'm going to do now is jump into Desmos, and we're going to start off with the base function f of x equals log x. Okay, so for now, there's a whole bunch of stuff written on the left-hand side. I don't want you to focus on it. I want you to focus on this beautiful blue graph here, which is the graph of y equals log x. Now, by default, that log is base 10, so just be aware of that. We can play with other bases here. We're just not going to right now. Okay, I'm now going to replace that by this very long version, which was the generic way of writing a transformed log function in um, generic notation with that a, k, d, and c. Remember, the a is responsible for vertical stretches and compressions and flips. The k is responsible for horizontal stretches, compressions, and flips. The d is responsible for sliding side to side, and the c is responsible for moving up and down. So I'm just going to turn that one on. It's going to be purple. I realize it's pretty close to the blue, but it's now purple. And I'll turn the blue one off. And I want to let you know that I've set the A and K values to 1 each, so there's no stretches or compressions or flips. And I've set the D and C to 0, so there are no side-to-side or up and down translations. From there, we can play with each of those variables and see what it does. Again, I don't think there's going to be any big surprises here because well, because these are the same as they have been for all the other function types. So when I increase A, I stretch upwards. Now on the left, I realize it looks like it's stretching down because technically it is stretching up and down at the same time. Either way, everything's becoming much more vertical. And as I go to negative values there, you'll see that I get the same idea. It's stretching it, but it is now upside down, which is essentially exponential decay. Sorry, the inverse of exponential decay, since we're not dealing with exponential functions. Okay, I'm going to set that back to 1, and we'll play with k and see what happens. And again, k should tell us something about what happens horizontally. For large values, I'm expecting a compression. And it definitely looks like it is compressing or pushing into the left. And for smaller values, it's definitely looks like it's pressing over to the right. It got to the right or stretched horizontally very quickly there. And at k equals 0, something horrible happens because then we've just got 0 inside our logarithm, which breaks it. And for negative numbers, it flipped it to the other side, just as predicted. Okay, D, very straightforward, slides it left and right, just as we always knew it would. And C slides it up and down, like we always knew it would. Okay, so I've set everything back to its base things of the A and the K are 1 and the D and the C are 0. I'm now going to turn on another function, which is basically, again, just y equals log x. This is the red one. You'll notice I put a 1 and a couple of zeros in there just to kind of as placeholders, but they're not actually modifying anything. Multiplying it by 1, adding and subtracting 0 does nothing. The reason I'm doing that is I want to show you something neat that happens. If you look at this and compare it to the generic version, you'll notice it's almost the same, except there's no k value. There's no k value. And this is going to be helpful when we're modeling. When we model, having a k value and an a value can be tricky. We saw with polynomials. And here I'm going to show you that the k value, other than flipping, which we need to do, other than flipping, is not needed. And the reason for that, we're going to take our k and I'm just going to set it to an arbitrary value, an arbitrary positive value anyway. I'll just say, let's shoot up there. Let's go a little bigger, 5.6. So our k has compressed our equivalent of the red graph by a factor of 5.6, meaning that whatever the value is here, this is 5.6 times smaller, or 1 divided by 5.6, which is 0.183. So it definitely has compressed vertically, but I want to show you that I can make the red graph with no k value whatsoever look exactly the same by simply shifting it up a little bit. So if I shift it up by 0.5, it's getting a little closer. 0.6, a little closer. 0.7, almost there. 0.8, a little bit too large. I'm going to show you the trick. I'm going to set it back to 0 for just 1 sec. We know the value here is 1. We just have to check the value here. Sorry, the value at 1 is 0. The value there at 1 is 0.748. So I'm just going to change this to 0.748. And I think you can verify if I zoom out, those are exactly the same graphs. So it turns out with logarithmic functions, I don't need to worry about what the k is ever, because I can always fix it by adjusting the c value, by basically shifting it up or down. The only exception to that, of course, is if I do flip it, the only way to fix it is to flip that. But same logic either way. I can now play with the c value to make it go upwards and match that graph. Okay, let me set those back to 0 or reset everything again. There we go. Okay, the last little thing I want to show you, and I will admit that this is a little bit confusing, so just bear with me here because the result at the end is more important than the process to get there, but I do want to show you the process. Let's say that I choose an arbitrary value for A here. So I basically give it an arbitrary value for a vertical stretch or compression. So I'm just going to go up here to 3.2. In the same way that we could get rid of the k by simply sliding it upwards and changing c, we actually can get rid of a as well. And I'm going to go back down to my red graph here. I'm just going to erase that one at the front and show you there is no a there. And I'll show you how you can match the graph. And it's in a kind of a weird way. And we're going to do it by trial and error because this calculation is not something you want to try in your head. But beside the log, I'm going to hit shift and negative, or shift and minus sign. And what it's going to do is allow me to enter in a base other than 10. So I'm going to actually just type in 10 for now to make it look exactly the way it looked before. But I want to show you that if I modify that base a little bit, I can actually make the purple graph. So I'm going to do this just by trial and error. I'm going to change the base from 10 to 5. That didn't quite work. How about 6, 7? Sorry, I'm going down, not up. 5, 4, 3, 2. Okay, 2 is a little bit too much. So 2.1, 2.15, 2.05. Okay, so this is trial and error, so this is not going to be perfect, but I think you can see that those are, when we zoom out, pretty much the same graph. There will be a little rounding error because we are doing approximates, but I think you get the point. So what that means is that I can get rid of an a value by changing the base. So here, instead of having an a value of 3.2 with base 10, I get the same graph with an a value of 1 and 2.05. And is that confusing and hard to do? Absolutely it is. But it's the reverse of that that actually is going to save us time. When we're dealing with a logarithm, we can go backwards. It doesn't matter what base it is or supposed to be. We can always express it as a base 10 log by just giving it an a value or a leading coefficient. So what that means is that all all logarithmic functions, regardless of what their base is, can be expressed this way with a base 10 log. We just have to modify our a value. So if you were wondering how do we model logs that don't have base 10, the answer is we pretend they have base 10 and correct that with a value for a. So similarly, if I wanted to model something like something with log 14. Okay, that might be the real equation that we're dealing with, but if we're trying to come up with a model in this form up here, the purple one, what we can do is play with the a until we make it the same. So I don't know, is a going to be bigger or smaller? Let's try 2. That's a little bit closer to the red one. What about 3? No, I think 2 is closer. Well, what about 1.5? 1.4, 1.3, 1.2, 1.1, 1.05. Oops. We're starting to get really close there. 1.04. 3, 2, 1. Okay, so we're getting closer and closer, but we're kind of getting closer to 1 doesn't do anything. Well, maybe that means it's just less than 1. Maybe our a is 0.9. Well, that's pretty close. That's pretty close. But maybe we can get even closer. 0.8. That's a little bit too far. 0.85. 87. 88. Yeah, maybe 887 works. 0.87. So either way, the moral of the story here is that you can actually model any base function using a base 10 logarithm. We just have to modify our a value. So we don't need a k because we can slide it up and down using c. So really, get rid of the k. Guess we can get rid of those brackets then. We don't need a base because we can fix it with a. Do we need the d? There's a question. And I think if you look at it, the d completely changes the vertical asymptote. So it turns out, yeah, we actually do need the d. There's nothing that can approximate that or fudge that. But we can get rid of the base and we can get rid of the k. And that itself is pretty useful. Okay, so I am going to leave you there. And as you can see, there are several questions at the bottom there that you can try to practice this. If you've got trouble with them, let me know. Otherwise, I will see you in the next lesson, which will probably be longer than this one. Later.